Section 11.5 deals with alternating series. An alternating series is a series where the terms alternate between being positive and negative. This example is an alternating series. If we start writing out the terms, I'm going to put my n's up top. So starting with n equals 1, 2, 3, 4, 5. That's enough. So the negative 1 raised to the n, when we raise it to an odd power, we're going to get a negative. And let's see, for n equals 1, that's negative 1. When we raise negative 1 to an even power, like 2, we get a positive. So we get plus 1 over 2 squared, then minus 1 over 3 squared, plus 1 over 4 squared, minus 1 over 5 squared. And this is alternating because every other term, the sign changes. Now, I'm going to change one little thing about this example to get example 2. Right here on the n, I'm going to change it to n plus 1. And it doesn't really matter that it's plus or minus. All that's going to change is the signs of these terms. So now when n is 1, we get negative 1 raised to the 2 power. So this is going to be positive. Then when n is 2, we get negative 1 raised to the 3rd, so negative. Like that. Now, most of the time, alternating series are going to have a negative 1 raised to an n plus 1 or an n. So sometimes they'll have n minus 1 instead of plus 1, but that doesn't make any difference. It still changes odd to even and changes where your pluses and minuses are. There are some other ways to get alternating series using sines and cosines, and there's probably other ways to do it, but for the most part, alternating series that we're going to work with are going to have these negative 1 powers in them. So let's look at the alternating series test. The alternating series test says this. If we let b be positive, bn is positive for all n's, 1, 2, 3, and so on. And we're going to build an alternating series like this, putting negative 1 to the n plus 1 times bn. Now the reason the b's had to be positive was because that way we know we don't have to worry about the b being negative and somehow messing up the sign. That way we're going to have plus, minus, and so on. The alternating series test tells us that if bn is less than the alternating series test tells us if bn is plus 1 is less than bn for all n, or in other words, the terms are shrinking in absolute value, and the limit of bn goes to 0 as n goes to infinity, then the alternating series converges. Let's look at why this works. There's a proof in the book, but I just want to give sort of an intuitive idea. Let's say you're starting out, here is 0. Here's the number line. Starting out with 0 here. Now let's say we have an alternating series. Well, if we start at 0 and we look at the partial sums, the first partial sum is just b1. So that's going to go from here over to here. The length of this thing is b1. Then we subtract off b2. So I'm going to go backward from there, some amount b2. And so this is my second partial sum. This is S1, this is S2. Now when I add on, and notice S2 doesn't go all the way back to 0. because we know that these lengths, B1, B2, they're shrinking. So B1 goes over this distance, B2 goes backwards some smaller distance. Now, I'm not gonna write the rest of these in because it's gonna get really messy. But if I add B3 onto here, B3 is gonna go over, but not as far as we came back before. So S3 is here. S4 is going to be back over here somewhere. Now the actual sum is going to be somewhere in the middle, the sum of all of them. The interesting observation here is for any two partial sums, I guess I should say consecutive partial sums, the total sum is in between. This is the alternating harmonic series. -1 to the n plus 1 over n. N goes from 1 to infinity. You start listing this out. The first term is 1. And the first term is positive because you get -1 raised to the 2 power. So you get 1 plus, or not plus, 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, etc. Now you can look at these terms and tell that they are shrinking and they are going to 0. So therefore, by the alternating series test, they converge. So we just saw that the alternating harmonic series will converge. Let's look at the sums. Over here, I put this into a spreadsheet, and we can see the different terms that we're adding on, and then the partial sums over here. So the actual sum, if we come down to the bottom and look at it, the actual sum is getting close to 0.69 something. Earlier, recall, I said that the actual sum is always between any two consecutive sums. So when we get down to here, we can be certain that the actual sum is in between 0.69628 and 690, etc. If you look at this 160th term, it's 0.006. Notice adding that on doesn't affect the third decimal place. I'm sorry, it doesn't affect the second decimal place. So we know that S is the sum of 0.69 is accurate to 2 decimal places.